Hello. Thank you. I'm also going to talk about auxetic structures as my colleague did before, but with a different focus. I'd like to present a computerized design method which can simplify the production of free-form reinforced concrete components to build doubly curved shell structures. That's my idea. Digital methods in architectural design have produced an increasing geometric complexity in recent years, which in many cases requires a challenging formwork for this production. Let's start with looking at some existing approaches. One approach is 3D printing, as we have seen today as well here. 3D printing of concrete, but for building, in fact, we need reinforced concrete, as we can see on the right side. So this is not a satisfactory solution for our goal. Another approach is the project melt direction. So, other approach is, and all of us will know this project, mesh mold by Gramazio Cola. It combines formwork and reinforcement into one single system. But the problem here, it is a highly complex and exacting production process. And our question is, might it not be possible to find an easier way to produce such a complex shape? It might. Looking back, a few decades back, we find pioneering shell structures that already combined form setting and reinforcement into one structural mix. Most of us will know this example from Pierre-Louis Genervi and his invention of the ferrocement. Another example is shotcrete from Ulrich Müther. He's an Eastern German architect, and he invented in the 1960s the TOCRET system, a system of spraying concrete on a steel matrix, seen on the left side. Most of his buildings, like this music pavilion, are doubly curved shell structures. This is a good start. However, producing such a three-dimensional matrix stays cumbersome. So what we are looking for? We are looking for a three-dimensional structure which can serve as lost formwork and reinforcement. But it should be easy and cheap to produce, ideally as an automated process, and without the necessity of spatial weave the three-dimensional mesh. Is there a way to use computational resources we have nowadays to translate all the three-dimensional information into a two-dimensional structure so that it can be manufactured in 2D? That's the question. And in fact, there is. And again, the auxetic structures. The key lies in this, exactly in this auxetic structures. But I will try. So it's similar to that what Riccardi told us before, but I want to focus to another point. So first, to remind ourselves, auxetic structures on a macroscopic scale, like here, are flat materials with specific incisions, allowing for negative transversal stretching. This means, and that is important to us, they are stretchable in both dimensions, as we can see here. One example, another one Riccardo showed us before, for an auxetic structure based on a triangular mesh, showing the process of stretching. Auxetic behavior on a macroscopic scale is facilitated by specific incisions, as you can see there, in the material, while keeping significant vertices connected, thus forming kinematic linkages. The incisions expand into polygonal openings, and each area containing incisions turns into a grid-shaped matrix. The image documents the deformation of the of this auxetic structure. It is the geometry of the structure that warrants kinematic movement. So and now comes our definition. When the incisions follow a regular pattern and all cuts are identical, like in this example, we call this a regular auxetic structure. And here comes the interesting point. By stretching this regular structure uniformly, this means transversally, every expanded regular auxetic structure results in a unique corresponding flat geometry. So we start from the left and receive the right side. But there's another way to stretch the structure locally. This means normally to the plane. So before we did it transversal, and now we press it normally to the plane. In this way, the structure becomes spatial, as we can see on the right side. This is exactly what we've been looking for. But there remains a problem. One regular structure can result a multitude of spatial forms, like the following examples. So we start with this regular structure, regular cuts all over the whole plane, and we can receive that one, that shape, or that one, or even that one. But just notice here, in this example, some parts of the structure are already fully stretched, like in the middle, others are not. I will come to that back later, because this is the important point. So again, we have a basic way of producing multiple 3D shapes from one single 2D auxetic structure. This has been the current way of thinking about auxetic structures so far. Our challenge is to figure out how to compute the specific pattern for a 2D auxetic structure that will lead to our one 3D target shape, and only to that one. This is what we are looking for now. We need to rethink auxetic structures to solve this problem. Our approach puts the focus on that expansion process and its intermediate steps. When a structure has already been stretched to a certain extent, like seen in the middle, the further potential of the expansion is limited. In these partially stretched structures, the incisions are showing up as polygonal openings. Hence, the potential for expansion is determined by the type of incision patterns, cut or polygonal opening. Straight cut means high potential for expansion. So if we start with a cut, then we have a high potential. Or polygonal openings. If we start with the polygonal openings, means we have just a lower potential for expansion. But it is only, and this is the second important point, but it is only in its fully expanded state, like seen on the right side, that the auxetic structure takes a final definitive shape. To improve the control over the deformation process, our innovative approach is to use already modified patterns as our next starting point. Instead of straight cuts, where we started on the upper row, we're performing polygonal cuts in the flat material. On the left side, they are both based on the same mesh, resulting in an auxetic structure with a lower but clearly definable potential for maximum expansion. In other words, varying between straight and polygonal cuts gives us precise control over the deformation and thus over the size of the fully stretched structure. Like seen here. So we are only changing the type of incisions. When the variations in incision patterns is applied globally to the whole structure, as seen in this animation, we still call it a regular auxetic structure. In their fully stretched state, all of them will remain two-dimensional, as in the example before. Let's now apply local deformation on auxetic structures with globally varying incision patterns. So we have two different globally varying incision patterns on the left side, and the result on the right side. So remember that we are looking at limiting the expansion potential in order to better control the deformation. In the second example of the spatial deformed structure, we already detect some areas in the middle that are fully stretched. But what we want is an auxetic structure fully stretched at every segment, like shown on the right side. Only this can represent our target shape. This can represent our target shape distinctly as described before. So we are looking for a 2D auxetic structure for the right example. The question is, starting from a fully stretched auxetic structure as 3D matrix, what is the corresponding 2D structure? The key answer lies in local variation of incision patterns. A variation in incision patterns cannot only be applied globally, as before, to the whole structure, but also more locally at the level of the individual cuts. This is part of our innovative approach. We call this an irregular auxetic structure. As you can see on the left side, we start with an irregular auxetic structure, varying incision patterns, and on the right side, the fully stretched 3D result. Bingo. We can now find the unique corresponding 3D structure for our target shape, because an irregular structure stretched at every point to its maximum results in a distinct spatial shape. I repeat this, an irregular auxetic structure stretched at every point to its maximum results in a distinct spatial shape. That's what we wanted. Let's now look how we can make this happen. The core of our innovation is to design the incisions for each facet individually, as said before. This allows us to determine which specific flat auxetic structure is in its fully expanded form produces our target shape. We have developed an integrated process in which the variations of the incisions is automated as a function of a target shape. We start with an architectural model as a computationally designed shaped, as seen on the right side. Here is the possibility for an FE analysis. We can optimize the form with this. The result is our target shape. To make it scriptable, we have to translate our target shape in a mesh. At this stage, a discrete conformal 2D mesh has to be generated. So we start with the 3D mesh in the middle, left side, and we create a conformal two-dimensional mesh. To do this, there are several computational methods to do so. We used Verilab for this process. 2D and 3D mesh can now be compared with each other to assess the necessity of degree of deformation for each of the corresponding mesh faces. You can see this if you have a look at the red triangles. These are the faces which can be compared to each other. This serves as a basis for the size of incisions making up the auxetic structure. In the case of large differences between corresponding mesh faces, that is where the auxetic structure will need to be highly extensible. Extensions will have to be smaller. Where smaller differences in size appear, like in the corners of the structure, hardly any expansions is needed. Incisions resemble widely open polygons. The data generated by comparing all the corresponding mesh faces now feeds into an algorithm. This is the core of our workflow. It computes a qualitatively correct auxetic structure for a given shape. To get the quantitatively correct auxetic structure, we need to introduce an iterative evolutionary process. The auxetic structure is modeled as folding, as you can see on the left side. In the next step of our digital workflow, we use dynamic relaxation, right side, to unfold the computed structure. The auxetic structure falls into shape through relaxation. And now the iterative process has to start. After relaxation, we check the conformity of the generated auxetic structure with the target shape. In an evolutionary process, a new auxetic structure is computed with slight modifications, then relaxed again and again and again. This iterative evolutionary optimization process will deliver a range of two-dimensional auxetic structures, each more closely approximating the target shape. And here are the modified auxetic structures in 2D and their relaxed form. You can see that we are getting closer to determining the auxetic structure best approximating the target shape. To remember the examples from the beginning, here are the corresponding 2D structures computed with our algorithm. It can be applied to surfaces with negative or positive Gaussian curvature as well. And that is the solution we've been looking for. We've reached the end of our geometrical research, and now we start a new adventure exploring material. Just another 2 slides. Just to give an example what we are doing now. We first are thinking about anisotropic textile membranes to build our auxetic structure from, in combination with resin impregnation. It can serve as a 3D matrix for shotcrete. Or next point could be working with steel metal. The auxetic structure is produced by means of laser cutting. The subsequent 3-dimensional structure of the auxetic structure can be done through robotically controlled gradual distortion. No need for complicated 3-dimensional weaving like in the examples of Nervi, Mütter, and Grammazicola. This will be our next steps. I think I have to finish now. Thank you.